This whole story started with these famous Rasmus-Stroganov conjectures, which in fact is normally called the Rasmus-Stroganov conjecture, but there are in fact many of them. It exists in several declinations that it is a good thing to organize in wide classes, but they are spread over a number of papers, of which I give a list here, hopefully without forgetting anybody. And they've been formulated in the early 2000s, and they relate the probabilities of certain connectivity patterns in two different integrable models. On one side, the O1 dense loop model, and on the other side, the fully packed model. These models are both integrable, but they are different. They have different values of these. I mean, all the things that classify the type of phase transition, they have different. And they are also different in spirit. And I'm talking about O1 dense loop model and fully packed loop model instead of talking of their equivalent formulation in terms of XXZ quantum spin chain and 6-vertex model, because these are the formulations in which you see well these patterns of which you evaluate probabilities. But most importantly, these are models at a given special values of delta, for example, for the 6-vertex model, or n for the ON dense loop model, at which combinatorics comes into the game. And you see that certain things which now we call, in a vaguous way, combinatorial points arise. So, this is a quick introduction to our observable. Our observable will be link patterns. A link pattern is a pairing of two endpoints without crossing if they are on the boundary of a disk. So this is typically a link pattern. What is not often said, but will be important in my talk, is that these guys are in bijection with so many things, among which the paths, which are also interpreted as integer partitions, boxed into the triangular integer partition n-1, n-2 up to 1. For example, this integer partition is 3, 3, 1, which is the one that is in correspondence with this matching, which is 1 to 6, 2 to 3, 4 to 5, 7 to 10, and so on. So keep this in mind. Let's start with the O1 dense loop model. You have a semi-infinite cylinder with perimeter 2n. You fill it with these two tiles, just with, say, equal probabilities. And you have configurations like these. And here, you forget about all the small loops, which are infinitely many, and you follow just the arcs that touch the boundary. And these make for you a link pattern, which is here. For example, 9 goes up to 12, 9 goes to 12. Very well. You pick up a random configuration, you annotate the link pattern, you have probabilities for this link pattern. And then you do a similar game on this other model, which is fully packed loop configurations on the n times n square, in which the boundary conditions are alternating black and white, as you can see here, which in the 6-vertex model accounts for domain wall boundary conditions. And similarly, you define a link pattern. Here you go from 9 to 2, so I have a long arc from 9 to 2. You could ask, what's the rule again for the loops? The loops, you forget about it. You could ask, yes, but you have black and white, so you may also look at white. I don't do that for the moment. So that's the rule. And the conjecture just states that these two sets of probabilities are equal. Nothing more, nothing less than that. So this first kind of conjecture has been conjectured in 2001 for the square. And me and Luigi Cantini, who's also here, had a proof for this, not only for the square domain, but for a variety of domains. in which something happens that we classify as those that we now call the dihedral domains. In all these cases, we can prove that those probabilities are proportional. And now there is a sanity check. How could it be possible that these two vectors are equal when, in principle, this equality holds at side for psi tilde, the vectors on the cylinder, which means a connectivity pattern pi has the same probability as all of its rotations, but it's not at side true on the square. For the conjecture to be true, it must in particular be true to this equation, and this bizarre property of this counting of configurations on the square is known like Wheeland gyration. It is a bijective property proven by a bijection invented by Ben Wheeland, actually earlier than the Rasumo-Stroganov conjecture in 2000. So, very well, the conjecture has some hope to be true. In fact, it is true, it is proven. This Wheeland gyration has been a main ingredient in producing a proof of this conjecture, and once you have it, you look at what's the natural setting in which the gyration holds, and you find out that, for example, a three-bundle domain is also a situation in which it holds, and in fact there is this proportionality. 1, 1, 1, 2, 2 for the square is just proportional to 2, 2, 2, 4, 4 on these three-bundle domains. So, as I was telling, we have this Wheeland gyration, and the Wheeland gyration lemma is a statement concerning, at the same time, the black link pattern, the white link pattern, sorry I use red because I cannot use white, and the total number of loops, black and white altogether. However, we have never been able to use Wheeland lemma in its full power because we wouldn't even reach 3 times the refined conjecture to prove, because we don't have the triple refinement on the one. You could naively think that the Roder model, which is a two-color model which can project back to the O1 could, but there seems to be obstacle. We really have no candidates for doing this. We don't have a black and white Rasumo-Stroganov. Also, Stroganov-like conjectures which are not dihedral. For example, there is one famous simple one which is vertical, and is also being conjectured in 2001. So you can have now a strip instead of a cylinder with a boundary, and fully packed loop configurations which have a reflection. In that case, you have other vectors, psi tilde and vertical, MC and vertical, and these are also proportional conjecturally. Much. We do not have try to export the same idea of our proof. This other similar case says there should be again the idea that, like there are dihedral domains, here there are vertical domains which are many. For example, this bizarre one, which have these enumerations refined according to the number of U turns here, which are black or white, if you want. But we don't know how to cook of the Rasumo-Stroganov conjecture in this case. So let's go to the topic of today. Conjecture. Sure. Or means Well, yes, there is one bijection and the other one. And in order to produce the bijection here, you have to use one bijection on the even sides and the opposite one on the odd sides. Because white goes to white is the opposite of outgoing goes to ingoing. So it's a staggered bijection. If you have a triangle, introduces reversal points. But here we only have squares, so it doesn't matter. In that case, it's not bad. U-turns are two. They are polygons of two sides. And when the polygons are even side, you don't have the insertion of those points. So, but there are also other families that we will not see here in which this would matter, in fact. So we are here. I stressed already two failures of our old proofs. One, we cannot even invent black and white Razumov-Stroganov, although we have a black and white Wieland lemma. And we cannot solve the vertical Razumov-Stroganov conjecture in any of its declinations. And so what do? We do something crazy. We look at black and white loop refinement on the vertical domain, on one of the simplest vertical domain, which is the U-turn ASMs, which are just these. Crazily enough, you can list here in principle all the possible number of loops, which is some integer. Of course, it cannot be too big because there is not much room, but here it can be 0 and 1. And you could have this and this link pattern for the black and white. So say that this is this. In principle, you have 2 times 2 times 2, 8 possible rows here in this table, but only 3 happens. If here you have the rainbow, here you have the small arcs. If here you have the small arcs, you can have either the rainbow or the small arcs. And if you have the small arcs, you have 1 loop. Otherwise, you have 0 loops. Only these 3 cases occur among the 8 or in fact infinite possible ones. And if you organize your configurations according to the number of black U-turns here along this refraction wall, this can be 0, 1, up to n, you see that there are 3, 6, and 3 configurations here, which are exactly 1, 1, 1, 2, 2, 2, and 1, 1, 1 along these rows. This is just the first instance of something that you can see on larger table and see that there is something happening. And I'm going to collect here a lot of conjectures of this flavor. So first of all, let's organize these triple refined enumerations into vectors, into components like in Razumov-Stroganov. So we have pi black, pi white, tau to the number of loops, and white to the number of black U-turns. So this is a bunch of polynomials, Catalan n times Catalan n polynomials in the two variables tau and y. What we know is that if we put tau equal 1 and sum over pi black and pi white, we have the partition function of the U-turn uniform enumeration of alternating set matrices, which is something that we know. And in fact, we know from Kuperberg that there is an overall factor 1 plus 1 to the n. So me and Luigi, while we were studying this vertical Razumov-Stroganov, I'm hoping to prove it in the first place, we had this bunch of conjectures of where it holds, including this one, which means even if you sum only on pi white and keep pi black, there is this factorization. But little we could guess at those times that even the crazy things in which you don't sum even on pi white, we do the triple enumeration, which is normally bad because there is not even Razumov-Stroganov, Even in this case, there is a 1 plus y to the n overall factor, which is this fact that we had 3, 6, 3, which is clearly 3 times the binomial coefficients. If you try to devise a proof, maybe we are done, I don't know, but a factor 1 plus y is evident. A second factor 1 plus y, if n is larger than 2, is tricky but doable, and we, at the moment, cannot do anything else. And this is just the first conjecture of the many to come. So, let's take this conjecture for granted for a while, and so we can take just the coefficient y to the 0 and forget about black U-turns completely, and have just the white U-turns. We can arrange them into these Catalan times Catalan tables of polynomials in tau, where tau counts the number of cycles. So here you have a loop and you put tau. Here you don't have loops and you put 1 and 1. And here there is a 0 because there are no configurations. The same in size 3. If you do the same in size something useful for what follows is that you can use this bijection between link patterns and integer partition and put the tables with integer partitions. And I'm noting here the number of boxes into the partition. You can do the same in size 4 and get this big table. And you stare at those tables, we have them up to size 6, I guess, and you realize that, well, this is just an example, many things. First of all, this polynomial have a very simple degree formula, which is size of lambda plus size of rho as integer partition minus. In particular, they vanish if this expected degree is negative. Third conjecture, these polynomials are of defined parity, even or odd, depending on the degree. Fourth conjecture, the tables have 3 involutions along the diagonal, and you can swap rho with rho prime and lambda with lambda prime separately. The first is proven easily by using the one Wieland operator that we have here instead of 2, plus swapping black and white. The second will be an easy corollary if we had already conjecture 1, because it will change the power y to the k, power y. But the third one is mysterious. Let's have a look at the table. It's instructive. You see what I mean? Not only this table is symmetric along the diagonal, but also has identical column. For example, this column, which is the partition 2, 1, 1, is the same as this column, which is the transpose partition 3, 1. And also 1, 1, 1 with 3. They are also equal columns, and so on and so forth. Same for the rows. And big conjecture, the one that when the degree is 0, the entries are just integers. And these integers are the Litovo-Richardson coefficients. So a bunch of 1s up to here, and here you already have a 2, for example. And there are, again, big numbers, but many numbers. So what are the Litovo-Richardson coefficients? Many of you already know, but review because we want to understand, ultimately, what could be the other polynomials. So we better first understand what these Litovo-Richardson are. So, integer partitions, we already seen them a lot, are just the fillings of these Young diagrams with numbers, which are weakly increasing along rows and strictly along columns, and these are called semi-standard Young tableau, which are something that appears in the representation theory of the general linear group. Sure polynomials are just the generating functions of semi-standard Young tableau in a sense. Every time you have a tree, you put a factor x3 into a monomial, and then you sum over the tableau, and you get a polynomial. For example, this monomial is associated to this tableau, and this is its contribution to the sure polynomial in x1, x6 for this diagram. Very well. These polynomials are homogeneous of degree, which is obvious. They are symmetric. You can see that directly through something which is called the Bender-Knut involution. They form a basis of the algebras of symmetric polynomials in n variables, once you restrict to the partitions which have most. Then there is a nice formula called the Weil character formula, which tells that not only they are symmetric, but they are symmetric also because they are the ratio of two antisymmetric functions which are determinants. The formula is this one. And then there are other types of symmetric polynomials. You have the algebraic basis given by elementary and completely homogeneous symmetric functions, the e's and the h. So the sure are polynomials in the e's or in the h, and once you have polynomials in e or h, choice of the, for example, you have these famous Jacobi-Trudi and dual Jacobi-Trudi formulas. There are other types of determinants in these e's, h, and e's, and so they stabilize in the sense that they become independent on the choice of the alphabet, on the choice of the size of the alphabet. So in this case, you are talking about sure functions instead of sure polynomials, because they are defined and well defined, even if there are many possibilities of infinite alphabet, and some which are especially useful to our purposes, which are the supersymmetric alphabets. Supersymmetric alphabets we will denote with x1 to xn, which are the normal ones, then a bar, y1, ym. y1, ym are and strictly smaller. It had to be an infinite alphabet. You can define them either as supercharacters of the GL and M, or through the Jacobi-Trudi formulas by taking these other expressions. And the symmetry with this Homer involution symmetry also tells you that sure or skew sure, actually the skew sure I haven't introduced that so far, have an involution. You can swap these bosons and fermions and reflect the diagrams. And that one is the same expression. So the skew polynomials are something handy to have. They are not required to construct the basis because the sure already are a basis, but they are useful in principle. And you define them with the same idea of generating function on semi-standard Young tableau on the difference, set difference among two partitions. For example, this minus this is this diagram. You fill it with numbers with this weak and strong increasing, and then you make the sum. And these skew functions, they also have Jacobi-Trudi and dual Jacobi-Trudi formulas in which you have mu inside. An interesting fact about skew sure function is that if you consider normal scalar product with a delta, Kronecker delta, then the skew sure is just making a normal sure jump on the other side. You have this. Very well. Skew sure functions have a natural property. You can split alphabets in two by using them. This is just an obvious bijection. If you have a finite alphabet, but the probability passed through to infinite alphabets. And then here they are, our famous Littlewood-Richardson coefficients. They are non-negative integers, it was not guaranteed a priori, which enter in the product formula of the functions. I said you that the Schurs are a linear basis in the algebra of functions. So you know how to make the sum because that's the basis. So you only have to learn how to make the product of the to characterize the algebra. And now an interesting fact is that because Hall scalar product and Schur function are self-dual with that scalar product, the Littlewood-Richardson coefficient enter these three problems. How do you make the product? How do you expand skew functions? And how do you split the alphabet? If you want to keep the same philosophy, you can study other polynomials, which are kind of similar, but different. For example, Hall, Littlewood, Grothendieck, and so on. Single property drops. These bases are not self-dual in general. Normally, you will have a basis F and a dual basis G. We will use some Einstein notation all along in this case. And then we will have structural constant for example, for the product of F and for the product of G, which are different. I will keep the letter C for one of them and use D for the other. Here, you will have C in certain cases, and depending if you're using F or G, and one or the other property. Very well. Here we are with integrated systems. Also, Schur polynomials are vertex model. Very simple one, free fermionic vertex. How do you do that? First of all, you introduce these Maya diagrams, these black and white dots that correspond to vertical and horizontal steps in the profile of lambda and mu. So you put mu below, lambda above this strip whose height is the number of variables that you can have. And then if you have a green losange at height 4, you have a factor x4 in your Young tableau and then in your generating function. So the partition function of this strip with this boundary condition lambda and mu and these horizontal spectral parameters x1 to x6 is exactly the Schur polynomial Schur lambda mu x1 x6. Very well, losanges are nice, but in order to build up the supersymmetric version of the Schur functions that we will later, we better tilt the triangular lattice into a square lattice. And we have two ways of doing that. We either take this 30 degrees to 0 and introduce weights that you can check that are the good weights, or you tilt it to 45 degrees and use the other weights. Now, why do I have these holes here and here? Because I've done a drawing with blue that comes from the blue and red path in this Gesell-Viennow-like stuff. Only these configurations are just special cases of the 6 vertex model configurations in path representation, and here there is one A vertex missing. So these are free fermionic 5 vertex model transfer matrices. This and this. Now with a B missing, and before with. And now the supersymmetry in a very simple recipe. We had omega involution switches lambda with lambda prime. Here it means that you have to make a T-bar transfer matrix just by taking your weights and tiles, you reflect the tile, swap blue and red. By this recipe, of course, this is going well by telling that you are swapping the alphabet and taking the transpose integer partition. This is the recipe for doing supersymmetric Schur polynomials. You take a bunch of T transfer matrices for the boson and T bar transfer matrices for the fermions and take the contributions. And luckily enough, similar stuff for, and you construct a U bar with the same recipe and you get the very same function and skew functions. So this is what I was saying. The famous description in algebraic combinatorics is that the transfer matrix lambda mu lambda element is non-zero only if lambda minus mu is a horizontal strip, whatever it means. It is written in the tiles in a sense, and in that case it's just a power of x or a power of y in this case if it is a vertical strip. And you have a nice bracket formalism with operators that tells you that skew-Schur functions are just a bracket of these operators. You have also transpose operators that are just a transpose, and T bar and their transpose form a very nice algebra and have an obvious action on the vacuum vectors. And by this, you can calculate several interesting partition functions, which is something that is now called Schur processes. Very well. Up to now, things that you may have heard about and are simple, sure. But here, there is a very intelligent new ingredient, just been done by Paul since just 10. He realized that also the Littlewood-Richardson coefficients are described by this time of higher rank, which means you have particles of 3 colors. There was a previous work of Knutsson and Tao that was interpreting the Littlewood-Richardson rule as certain tilings of a triangle. And what prove is that, for example, if you take this coproduct identity, this one can be interpreted as a commutation of transfer matrices in this SL3 model, and in which the Schur factors enters into the 3 possible embedding of SL2 into SL3. And these pictures, in a way, this is a bunch of T bar and T transfer matrices and certain T0 transfer matrix. And in this setting, there are many paths which are frozen, and here you have a supersymmetric. And then you commute them, and what turns out is that here you have a Knutsson-Tao puzzle, other frozen parts, and the normal Schur that you had in this coproduct. Beautiful idea. Once you know it, you have the idea. And so keep this in mind when we want to now understand the other polynomials. Let us go back to our conjectures. We had several of them, which this one telling that you have 2 easy involution and a complicated one, and this one that tells that you have the Littlewood-Richardson coefficient when you have degree 0. Just like in Razumov-Stroganov, let's make a sanity check. Are these 2 conjectures compatible? Have you ever heard about Littlewood-Richardson coefficient being invariant under reflecting only one of the indices? This seems to be unheard. I ask you, let's define the class M of magic lambda diagrams, which are those for which you can swap nu for every mu and nu contributing. Is this set M empty? Because we know that for our conjectures to hold, the 2 of them, M should contain the set of triangular integers. Otherwise, it's think the triangular integer partition are actually those which are also magic. I can even give you a proof of it. One of the direction is really easy. You construct two entries which are different, and so you conclude that a non-triangular one cannot be magic. And then triangular is equal to magic because these transfer matrices have the same action on triangular diagrams. Set like ways. Horizontal strip from a triangular integer partition, that one is automatically. When you have a recipe on the branching rule, which is automatically symmetric on delta n, then you have a triangular equal magic lemma almost for free. This is not confined to Schur. This is true for every branching rule with this symmetry problem. Well, the proof is here. It's a bit tedious to read. You have to do that carefully, but you conclude that it is. And so, I have all the ingredients for starting to think if there are deformations of Schur polynomials that may possibly also give predictions for all polynomials of higher degree in our U-turn exam tables. Hopefully. Let's see what it gives. Try to search, but we will search under the lamp. Know how to do vertex mod. Whatever, are in several places, but we to search among deformation of the free fermionic vertex models, because those are deformations. So you can turn this. If we do that in the systematic way, we search for solution of this RLL equation, and we find that there are things that tells us that we don't have to make the full-fledged search. Many things are fixed. Those green ones are fixed by the fact that we want the weight to be well-defined on infinite strings. On infinite strings, we have a bunch of vertical stripes, blue and red. Those weights must be 1, otherwise it's not well-defined. So this fixes 2 entries. Then we have a gauge invariance. This type of C and C prime vertices always come in pairs. So you can fix one of the weights to 1, and I did it here. And then you have a choice of who really is the spectral parameter. So you have a covariance and a reparametrization, so that you say, I will keep calling these x and y and see what happens to the rest. So you end up with only a known function. Analysis is very simple. For the t's to commute with themselves and the t-bars to do and to commute with each other, you need to satisfy these equations simultaneously. Single obvious solution, which is to introduce a parameter tau, the shift. This analysis is exhaustive. This is the only thing you can do within 5 vertex model. And if you do that, you end up with these deformed versions of the branching rule that tells you that when you have an element which has the same value of the previous one along its row, instead of having its variable, you have its variable minus tau. This is the new rule, which is the new rule on the vertices. The configurations are the same. They're just. And this gives you some new polynomials that I will call f. Much fantasy. So the f are homogeneous in x, y, and tau. So tau actually is a trivial row. It can be reabsorbed. The only case in which you cannot reabsorb it is if tau is equal to 0, which is sure. But every non-zero case, it's equally well described by tau equal 1, which are these new polynomials, new for the time being. But the homogeneity also tells us that the structural constant cannot be polynomials. So we cannot opt for our ASM polynomials are exactly the new structural constant. The best hope is that they are the leading coefficient, because you can only have a monomial. And the degree is such that if it is something, it is the leading coefficient. In order to have polynomial, we need to break this inhomogeneity. We had a recipe with a 6 model, but it doesn't seem to guess the good polynomials, so I will not stress this factor much. So, long story short, you can find matrices B and B inverse that construct your new functions from the sure ones. They are very nice and they are still Lorentz-Standings. And then you recognize that these functions have wild type, Jacobi-Trudi formulas, and everything, and they are essentially a twisted version of Grothendieck polynomials. So the structural constants of Grothendieck polynomials may be there in our ASMs. I do the same for you, and what I conclude with is conjecture 6. This is the best conjecture so far. Not only we had little coefficient is the little Richardson coefficients of these Grothendieck ones. The conjecture holds up to n equals 5. And again, we constructed the model in such a way that the sanity check of the symmetry triangular equal magic holds because of the very same proof of before. So this is the conclusion. We have conjecture of increasing order astonishment. Don't have a clue on how to prove them. That's all.
Thank you, Andrea. Are there questions?
So I'm wondering, because for these Schur polynomials, it's about free fermionic 5-vertex model. And at the beginning, I thought that you're dealing with, in general, 6-vertex model, right? I didn't get the connection why the Schur polynomial would appear, or this Littlewood-Richardson coefficient would appear in the...
There is no good reason why it should be there. It's just that we find that it is there, empirically. Okay. Similarly, there is a similar spirit work of Paul-Justin that realizes that in certain fully packed loops in the triangle, he calls them, that arise when you study the Rachmaninoff-Stroganov components for diagrams which are a complicated Lie pattern and a big rainbow. Also there are little Richardson coefficient arising in a sector of the counting of configurations, and we don't know why. And this is, I believe that this is an emerging question. Why do we see things like this arise in a situation where they shouldn't be? In the very same sense that O1 dense loop model and fully packed loop models in the Rachmaninoff-Stroganov conjecture shouldn't have been connected because they are completely different models, yet again, shouldn't have little Richardson coefficients there. And we shouldn't have the enumeration of totally symmetric self-complementary plane partitions. So all these combinatorial facts are astonishing and, in our understanding, unmotivated. That's the surprise.
So at the start of your talk, in your tables, these Littlewood-Richardson coefficient appeared in the vertically symmetric cases, right?
In the, if you want, in the U-turn, but with y equal 0, it means that also they are there in the VS-ASM.
Yeah, so this is type B, and well, the Littlewood-Richardson coefficients are for type A, and Schur functions.
So I have troubles in type A, if you want, even at the very beginning, actually that's my first slide, maybe. You see, in the vertical case, it is obvious how to open the link pattern. But in the dihedral case, the link pattern lives on the circle. So even the relation with the lambda is natural only in the vertical case. Our second proof with the Razumov-Stroganov conjecture, it was for the monodromy matrix, and in that case, we have a natural starting point of the link pattern. But also in that case, it doesn't seem to work well. I don't know why. Shouldn't be there. Yet again. I know what you mean. Maybe there is something like this also in the dihedral case, but I couldn't figure it out.
This point delta minus 1/2 because it's an infinite temperature limit. So that's very natural that you enumerate things. So it is a combinatorial point from the point of view of 6 vertex model. So that you have combinatorial there, as the physicist, I don't find the astonishing.
Yes, but many things are combinatorial. For example, another nice domain in which vertical Razumov-Stroganov holds is this one. And actually, I have another bunch of unpublished work on this OS-ASM version of the conjecture. Many nice things happen here, but nothing like the tables I'm talking about. These tables, being nice in this sense, seems to be specific to that domain, and here it doesn't work. For apparently no reason. And maybe you say, but these boundary conditions are weird. But also, this case, the UUASM, doesn't work either. I don't know why USM are special. They shouldn't. It's against the philosophy of Razumov-Stroganov. Everything that I told you goes against the philosophy that I have purported up to the point when I started this work. I'm contradicting everything I've done in this topic so far. That's that.
This is a good attitude.
Well, at least I don't insist in doing the same error. I make new errors.
Other questions? If not, thank you again.